Hello, YouTube! Today we're going to be talking about how to read a position graph. We're not going to get into a couple of the things. We're really going to be working mostly, I think today anyway, with stuff that's got a constant velocity. We will get a little more complicated with this eventually, though. But for today, keeping it basic, really just talking about how do you use graphs in general, and then specifically how to use position graphs, and going from there. So, let's get to it. So again, really big, we're just describing the objective motion of an object. That's pretty much all of this unit. Instead of using the equations we've been using for constant velocity, though, we're going to see what that looks like on a graph. We're going to talk a little bit about the advantages of that and why you would want to do that, and then how to. So in particular, if you can look at a position graph and you can say, oh, at this time, x is this. Great. And if you can also say, like, at this time, x is this, and this is what that means, even better. If you can also look at one of those graphs and find the slope of the lines on that graph, and then also know why that slope matters and why we care about it, that's really good too. Other big ones are going to be finding total distance traveled and finding displacement, that thing that we did for the last two, doing those with a graph, and then also being able to find the average velocity and the speed from, again, a graph. Really, really, really important. And that's it. I guess it should be from a position versus time graph. I would say nx versus weird. Okay. So first off, why do we care about graphs? Well, the basic reason is just that graphs are really useful. Like, if you look at this graph, what it's showing you is not just where it is at 2 seconds, not just where it is at 4 seconds, not just at 6, not at any of these individual times. You actually also have this continuous information, meaning you can say literally any time that's on this graph between 0 and 15, any number between 0 and 15, and that'll give you the position at that time. Now, for this unit, we're only going to be dealing with graphs of things versus time, which means that there's some very particular ways that you can read them that are going to be incredibly useful. The big thing is that time only goes forward, right? So most of the time when you're looking at a graph, it's not necessarily about reading it in a certain direction, and it's not necessarily that the graph goes a certain way. But for these ones, what we're wanting to do is really just focus on left to right. So when you're looking at it, what's happening to the thing is progressively happening as you read from left to right. The y-coordinate for any of these graphs is going to give you the value of the thing. So when I say the y-coordinate, what I mean is that if we're looking at a place on this graph, so let's say the one that I already have highlighted, when I'm looking at this line, the thing I'm looking for to determine what's happening in the graph is going to be the y-coordinate, which in this case is position. The time is the x-coordinate. So if I'm asking you how big or small something is, how big or small it is this way doesn't matter because that's just time. It'll be at a specific time how big or small it is. Or if I'm saying what's the biggest position on this graph, the way you would find that is only by using how high or low it is on the y-axis, because that's the one that's really going to be changing things. Whereas the other one is just the time. Also, generally speaking, when we're talking about slope of a line or slope of a tangent line, which is something we'll sort of get to, what that slope is telling you is a rate of change, or the amount that something is changing by each time unit. In particular, for position, the slope will give us velocity, but that's spoilers. The way you find slope is by finding rise over run. If you have to do it with a best fit line, like if you've got real data, you would be making a line of best fit and then taking that line of best fit slope in order to find the thing. And in general, just get used to the idea that if you're trying to find a slope, it's probably going to be of real data. It's going to be of something of best fit, meaning you've sort of approximated what it should look like if it was smoothed out, and that's what you're using. Generally, the real thing is you're doing lots of statistics. So the way you find that slope is rise over run. take 2 points, figure out how high up the change in the y is for one of them, figure out how far over the change in the x is for another one, and then just take those two things and divide them. And the slope will always be the y divided by the x. And there's that delta again, meaning change, so change in y divided by change in x. Okay, so specifically for position and talking about the value of position. Honestly, this one does not mean a lot. When I talk about a graph being positive, or a thing being positive for this, what that's again talking about is the y value. The y value is going to be positive if it's above the line. So anywhere where this graph is, where the line from this graph is above the 0 line, that thing is positive. For position, that doesn't really mean a lot. It means whatever arbitrary point you picked to be 0. Remember how the last one I was just like, I don't know, the thing furthest to the left, let's call that 0. Like, it's not a huge deal. Whatever arbitrary point you picked to be 0, you're in front of it. If it's below the line, it means whatever arbitrary point you picked to be 0, you're behind it. Doesn't mean a whole lot. It's there, you know it, but because the 0 point doesn't super matter, plus or minus doesn't super matter. For velocity and acceleration, hugely important. We're not getting there yet, but part of why I'm bringing it up now is because it'll get more important later. Okay. My face is in the way. My face is not in the way. So the one that tends to matter more, and again for position not a huge deal, is going to be big versus small. Plus and minus don't tell you about big or small, just as something to be careful of. Plus just means it's in front of the thing. Minus just means it's behind the thing. So weirdly enough, if I am looking at this graph, going up from left to right does not mean it's necessarily getting bigger, because 0 is the smallest that the position can be, and 0 lives in the middle. Won't matter much for position graphs, will matter again hugely for velocity and acceleration graphs. A big negative position just means you're still far away from it, that's what the big part means, but you're behind it. A big positive position means you're far away from it and in front of it. So big positive stuff lives up here, big negative stuff lives down here, small positive and negative things live in the middle, either slightly above or slightly below the line. So one of the ways we can use this is to find total distance traveled or displacement. If you track how many boxes, or I shouldn't say boxes, if you track how much it goes up or down, that up or down value change will be your displacement, or alternately your total distance traveled. So if you want to find your displacement, just like how for all the word problems we were doing, or some of the word problems we were doing, you could be like, okay, well, I went this far during this section and this far in this direction during this section. I can take those and add them all together. That still works. And if you want to find the total distance traveled, you did the same thing, but if you didn't care if it was plus or minus, that works as well. So let's do a couple examples. So if we want to find our total distance traveled from 0 seconds to 10 seconds. Well, from 0 seconds to 8 seconds, from here to here, if I count it out, I go up by 1, 2, 3, 4, 5, 6, 7, 8. So this section here is plus 8 meters. For this section, from 0 seconds to 10 seconds, we haven't moved at all. We started out at plus 4, we ended up at plus 4. As an aside, another way you can do the displacement, and I'll do that at the end, but there is another way you can do displacement that sometimes is a lot easier. So if I want to find my total distance traveled, I take this plus 8, I take this 0, and I just add them together. I don't have to care about the plus or the minus, which gives me 8 meters. I'm not going to say plus 8 meters because I don't know, based on total distance traveled, that it was necessarily forward. For this one, doesn't matter much. For the next one, pretty significant. For our displacement, we do basically the same thing, except I'm going to be pretty explicit about saying that each of them is positive, and then I'm also going to say that my final end result was positive because I know, compared to where I started at -4 and where I wound up at +4, was ahead of that. For B, we're doing the same thing, but this time for the full 15 seconds. So you can do this for any subsection of time by just taking the times from, or the movements from that subsection of the time. So your total distance traveled, same thing. I do have to actually count out this next bit. So I start at +4, I end up at -246. So that means that I've gone down by 10. So this one is down by 10. For the total distance traveled, I don't care that it went down, it still went by 10. So I take the 8 from the first section, I take the 0 from the second section, I take the 10 from the third section, and I use that to be 18 total in motion. For the next bit, if I want to find my displacement, I can do the same thing, but now, because I'm trying to figure out where it is compared to where it started, it really matters whether or not it was forward or backwards. So I really need to include the minus. So that's the only real difference here, where I've got the +8, the +0, the -10, which gives me -2. There is one other way you can find the displacement, which might be a bit easier, which is to say, well, hey, displacement still equals final minus initial. So if I take my final, which is that it's down at -6, and I subtract my initial position, which was -4, that'll give me a displacement of -2. So that it's 2 under where it started. And that will work as well. There isn't something like that for total distance traveled. You do actually have to look at what's happening in the middle for total distance traveled. Again, off of earlier videos, because when you're talking about total distance traveled, you're talking about what's happening in the middle. Whereas for displacement, you could figure it out by looking at what happened in the middle, or because it's just describing the end results, you could use the end results. All right, so what else can we do with position graphs? The big one that's going to come up a lot, because this is going to be related to our other vocab words, is going to be slope. So because velocity is the rate of change in position, meaning how much your position is changing by each second, and your slope gives you the rate of change, if you take the slope of a position graph, that will give you your instantaneous velocity at that point in the position graph. So if I'm specifically trying to find the speed at 2 seconds, or the velocity at 2 seconds, all I have to do is find the slope of the line at 2 seconds. This gets weird if it's curved. So if it's something like this, it doesn't really make sense to say the slope at 5 seconds, because there isn't a slope at 5 seconds because it's a curve. But what we can do is we can say, all right, well, if I squint really hard and draw a line so that I'm basically taking a sheet of paper and like tracing it along the curve, or if I'm like, basically, I should use a different color from that. If I'm looking at this and I'm like, basically it's a line that kind of goes like this, the slope of this line will give you the instantaneous velocity. The way that you actually find that is using calculus, but for now, just to draw a line that roughly looks like it's going through the thing, kind of so that it like barely touches it, and then find the slope of that. Again, slope is rise over run, still works. And one other thing is that if you want to find the instantaneous speed, it's just whatever the velocity was, but positive. Or, sorry, don't care about the sign. Nice and easy on graphs. So, one of the things that's important about this is that if you're looking at a position graph and you're trying to talk about how the object is moving, the graph doesn't directly show you that. Remember, how something's moving is velocity. This is a graph of position. But because position is related to velocity, the shape of the graph, not the value of the graph, will tell you what the velocity is. Shape, in this case, being slope. So if your slope is positive, meaning that if you look at it from left to right and you move your finger along the graph, if the graph is going up like it is in this first section, that means your slope is positive and it's moving forward. The object is moving forward. I should be careful about using its. If the slope is 0 and it's flat, leveled out like this, on a position graph, that means that the object is not moving, it's still in that same place, it's stopped. If it's going down like this, the graph is going down, that means that the object is moving backwards because the slope is negative there. A steeper slope, meaning one that is closer to being vertical, is going to mean it's moving faster. That means that it's changing by more meters each second. You can actually see in this one the number of meters that it changes by each second. For a steep one, it's going by more than for a shallow one. If it's shallow, meaning closer to being completely horizontal, that'll mean it's going slower. The way you find your average velocity is actually the same way we were doing it before. You first find your total distance traveled using the sort of up and downs. You then find your time and you divide the two. The time is going to be like however much you've gone in the x-axis. So don't overcomplicate finding the time. If you're like, I want to find it from here to here, 6 to the right means the time was 6. Great. So let's do an example. So let's find the total distance traveled and displacement from 0 to 10. We've already done it. Great. B, we've already done it. Great. Find the average speed and average velocity from 0 to 15. This is where we start actually doing the newer stuff, where what we have to do is take that speed that we had previously had of 18, and now we divide that by our time, which, because we're asked from 0 to 15 seconds, is going to be 15 seconds. So 18 over 15 gives us 1.2. We can do the same thing with average velocity, but again, because average velocity uses that displacement, we'll use our displacement, so negative 2 over that 15. And that'll give us negative 0.13. So that is everything you can be expected to do with a position graph, unless there's acceleration. We'll learn about how to look at position graphs and tell what's happening with acceleration when we learn about acceleration graphs. But for now, that should, I think, be it. Thanks, and goodbye, YouTube.